Hello ladies and gentlemen, thank you for watching my video. My name is Satya Dasari. Currently I am doing my masters in University of Ottawa. Today I would like to discuss about expiration detection of perishable food using nanotechnology based gas sensor. By the end of the talk, I'll be leaving my email so that in case if you got any questions or if you want to know more about this topic, just drop me an email and I will get back to you as soon as I can. So before proceeding further, I would like to give you a brief outline of my presentation. The presentation is divided into 5 main sections. Firstly, I'll talk about the motivation that led the researchers to develop this sensor and also about some major problems that come with the food wastage. And then we will look at a smarter approach of monitoring the food expiry, that is without any human interference. And then I would like to move on to the solution for monitoring the food safety provided by the researchers, and next about the fabrication process for making the carbon nanotube based gas sensors, and finally we will look at the sensor tests by the scientists and the researchers on the carbon nanotube based gas sensor and how we can deploy the sensor in the real time and its working. Now I'll start by considering some facts and figures as shown on the screen. When I started reading the stats, I was really shocked by the amount of food that's being wasted every year. It's equivalent to almost 40% of the food that is being produced, and in terms of money, it's equivalent to $31 billion. In order to have a closer look at this problem, let's consider the stats in the pie chart. The pie chart is divided into 7 parts, pretty much covering the entire food chain process, that is, from the production to the consumption. The major contributor to the food wastage is the consumer, accounting for almost 47%. These stats shown on the screen are as of 2017. The numbers might have increased as of 2018. This leads me to the next point, that is the major problem associated with the food wastage. The first and foremost problem is hunger. In world, we produce enough food to feed everyone, but still 821 million people, 1 in 9, still go to bed on an empty stomach each night. Even more, 1 in 3 suffer from some form of malnutrition. It's all because of the food wastage. And the second problem is government is spending a lot of taxpayers' money for food wastage processing. And the next problem I would like to talk about is the global environmental damage due to the toxic gases released from the food wastage. And finally, about the global warming due to the increased carbon footprint. These are only a few major problems. To be honest, food wastage is a bigger problem than we think, and there is a strong motivation for researchers to find a solution for this. In addition, I would like to add the World Hunger Map provided by the World Food Program Organization so that we can understand the broader perspective of this problem across the world. This leads me to the next part of the presentation, that is the smarter way of monitoring the food expiry. Let's talk about the basics first. Degradation of perishable food is related to metabolic activities of the microorganisms, resulting in formation of gaseous compounds such as carbon dioxide. So monitoring the freshness and quality of the food can therefore be accomplished by monitoring the release of these gases in the food package. So the ideal smart solution for monitoring the freshness and quality of the food is to build sensors for detecting these gases. The technological solution provided by the nanotechnology researchers is to develop a sensor based on carbon nanotubes as sensing elements. Here we might have a question, why only carbon nanotubes are used for making this sensor? The answer to this question is it's because of the ideal properties of the carbon nanotubes, like low power consumption, low cost of production, and high sensitivity, as it has the high contact interface, making the absorption and desorption of the gas molecules easy. Now I would like to move on to the next section, that is the fabrication process of the carbon nanotube gas sensor. Here we are using the local synthesis technique for the fabrication of carbon nanotube based gas sensors. Again, we might be wondering here, like, why only local synthesis technique is the best approach. Usually the carbon nanotube synthesis requires a relatively very high temperature of greater than 600 degrees centigrade, but at that temperature exceeds the maximum temperature permissible for the CMOS devices, which in turn making the combination of carbon nanotubes and the CMOS technology difficult. But this difficulty can be overcome when we use the local synthesis technique, because we achieve the desired temperature here by using microheaters on the chip. Also, another advantage for using local synthesis is we can make sensors at very less cost so that it can be used by very large target groups. Now that we know local synthesis is the best approach for fabrication of carbon nanotube based gas sensors, let's dive into the local synthesis fabrication process without wasting our time anymore. Local synthesis technique was first introduced by Christian and Englander. Local synthesis of carbon nanotubes is done utilizing the principle of creating locally very high temperature, that is up to 900 degrees centigrade, at 0.4 bars of acetylene and argon atmosphere using a microheater on the chip. Here we use the acetylene gas so that the carbon nanotube growth happens at very low temperature than using any other carbon containing gases. The microheaters used here were fabricated using the Polymem's commercial process provided by the MEMSCAP. The temperature of the microheater was monitored by determining the resistance of the silicon bridge as shown in the image. This is the R bias which we are using here. Also, an external field between the two silicon bridges were created by applying an external voltage between them as shown in the figure. The purpose of using the external electric field is to align the growth direction of the carbon nanotubes. And finally, the local synthesis technique will allow the direct integration of the carbon nanotubes into the CMOS devices, potentially at a wafer level, to form a complete sensing system. The formed silicon carbon nanotube structure is tested as the carbon nanotube gas sensor, where the sensing element is the carbon nanotubes. Now, I would like to discuss about the electrical characterization of carbon nanotube gas sensor. The electrical characterization of synthesized carbon nanotubes indicated that the silicon carbon nanotube structure showing a diode-like behavior with a forward breakdown voltage of 2.3 volts as shown in the figure. Here, the change in IV characteristics of carbon nanotubes are characterized using a Wheatstone bridge configuration. I will be explaining more about the Wheatstone bridge in my next slide. So now, after examining the IV characteristics, we can conclude that the contacts between the carbon nanotubes and the silicon bridges can be modeled as resistors and diodes in series as shown in the image. As promised earlier, I would now like to discuss complete details about the Wheatstone bridge and its working. In 1833, Samuel Hunter Christian invented Wheatstone bridge, and later it was developed by Charles Wheatstone in 1843. The primary benefit of this bridge is its ability to provide extremely accurate measurements by balancing two legs of a bridge circuit. Now let's discuss more about its operation. In Wheatstone bridge, R1 and R3 and R2 and Rx are connected in series as shown in the image. As long as the ratio of R1 and R3 and R2 and Rx are equal, the bridge is in the balanced condition and there will be no potential difference across the galvanometer, and hence the current passing through the galvanometer is zero. In case if the bridge becomes the unbalanced condition due to some change in the resistance, then the R1 is to R3 will be not equal to R2 is to Rx. So that is the bridge unbalanced condition. Now that we know it's working, let's discuss more about how it's related to our project. When the carbon nanotubes are exposed to different gas combinations, the IV characteristics of the carbon nanotubes will be altered. So in order to derive the accurate values and see how it got impacted, we use the Wheatstone bridge here. Now that we have seen the fabrication process of carbon nanotube based gas sensor, I would like to move on to the next section of our presentation, that is the working of carbon nanotube based gas sensor. As we discussed earlier, the electrical characterization of synthesized carbon nanotubes indicate that the silicon carbon nanotube silicon structure showing a diode-like behavior, and the contacts between the grown carbon nanotubes and the silicon bridges are modeled as resistors and diodes in series. So here we are going to place the carbon nanotube gas sensor in a Wheatstone bridge as shown in the image, and then balance the bridge in the atmospheric conditions. So finally, this brings me to the complete setup of the sensor working. And now let's head to the sensor tests that the researchers choose to run on the sensor. Now let's consider the sensor test 1. Here initially the Wheatstone bridge is balanced in air, and gradually the air was replaced by carbon dioxide at 1 bar. We can observe a drastic change of Vg, that is the voltage across the bridge legs, suddenly drops from 0 to negatives as shown in the graph. This implies that the IV characteristics of the carbon nanotubes were affected, indicating the presence of a carbon dioxide gas. So let's move on to the sensor test 2. In sensor test 2, instead of using air, we will be using argon and carbon dioxide gases for testing purpose. The main reason for using argon gas here is because the inert gases are commonly used for modified atmosphere packing of the food products. So now let's get back to the sensor test. Initially, the Wheatstone bridge was first calibrated to be balanced in 1 bar of argon, and gradually the argon gas inside the chamber will be replaced with 1 bar of carbon dioxide. And here, as shown on the screen, there exists a voltage drop indicating the presence of carbon dioxide again. As we have noticed the sensor test results for sensitivity of carbon nanotube based sensors to different gases like air, argon and carbon dioxide, let's move on to the final part of the presentation now. The voltage fluctuations generated on the Wheatstone bridge are fed to the signal processing unit from where it gets recorded in the RFID tag. Here we can use either passive or active RFID tags. The nearest antenna records the readings from all the RFID tags in a particular region and inputs the results to the computer host where the computation happens and the users or the retailer is notified about the food. Let's summarize briefly what we have looked at. Firstly, we discussed about the motivation that led the researchers to develop this sensor and also about some major problems that come with the food wastage. And then we looked at a smarter approach of monitoring the food expiry, and then we moved on to the solution for monitoring the food safety provided by the researchers. And finally, we discussed about the fabrication process, the sensor test, and the working of the carbon nanotubes. Thank you all for listening. It was a pleasure being here today on this platform. In case if you got any questions, just drop me an email. I'll get back to you as soon as I can.